So, dispersion and reingestion of pollutants. And what I would like to present to you today is basically the work that we have been doing for the last several years in collaboration with IRSST. Now, to introduce the topic here, of course, everybody understands that air pollution is a major environmental problem. There are various sources of pollutants. I think it's very well known: combustion devices, motor vehicles, industrial laboratory facilities, office buildings, and so on. Common pollutants, there is a list here, but there are many, many, many more that you can see. Consequences, again, we all know that. There is a broad spectrum of acute and chronic, sometimes health effects. There are plenty of references, you know. These are just some selections here that they talk about respiratory diseases, cardiovascular diseases, and mortality. We are referring particularly on air pollution in urban areas, and some examples that I think they speak for themselves, whether it is traffic related or industrial laboratory kind of, related. There are accidental or non-accidental releases of hazardous materials in urban areas, which is our main interest. On the left-hand side, you'll see something, it's a hypothetical release of gas somewhere in Denver, and on the right-hand side is a Canadian, is in Toronto, an actual fire event that did take place. Now, more specifically, we're interested on the so-called episodic pollution and the reingestion of potential reingestion of pollutants on the adjacent buildings. Normally, you do have an adjacent building. You never have a building isolated in the middle of the desert or something. And of course, if you look into the history of these things, you're going to see previous references again, that this is just some examples. One case, 20% of the exhausted fumes re-entered the ventilation system of the building. Not very good if you are a worker in that particular building. In another study, more recent study, there was a report that ventilation intake pollution episodes in a daycare facility, they were so serious that basically the daycare facility had to be evacuated. Plenty of situations of reingestions. You can see some examples here. In fact, two of our city universities here, McGill and Concordia, are involved by looking at some of the stacks that they are on the roof of these buildings. We happened in our laboratory to be involved in the studies of both cases that you see here. In the case of McGill University, it was after the event. The building was already there. You recognize the building. The problems were there, and the question is to diagnose the problems and do something about them. At the Concordia building, which is on the bottom that you see there, well, the situation was better because we knew more at that time when it was built, so we did the study ahead of time. So we managed to make sure that we would not have these problems. And in fact, so far so good, I haven't had a single complaint. Now, why the adjacent building is really so important in dispersion? And this is a nice kind of, representation by using flow visualization. And flow visualization is something that everybody can see and recognize. It may not be 100% accurate, but it gives you an idea as to what is happening. So here is what's happening when you have a stack or an isolated building. And here is what's happening when you put a building in front of that isolated building. Again, if you have a little bit taller building and so on, you see how the plume, the pollutants, go upstream, which is not something that anybody is going to guess by just looking at that, but here is, the evidence as to what is happening. Now, based on aerodynamics, this can be, of course, explained, but nevertheless, this is something that it is of interest and it is of importance. Now, how do we assess the pollutant concentration? Because pollutants are everywhere. The question is how dense they are. Okay, what is the concentration? If it is a low concentration, which means high dilution, then perhaps, depending on the substance, perhaps they're not of great concern. If, on the other hand, they are of high concentration, then, of course, they're going to be problematic. So what do we have in our hands to assess the concentration of the pollutants? We do have a number of empirical models. I'll go quickly through those. Assay, EPA. EPA stands for the Environmental Protection Agency in the United States. Wind tunnel modeling, which we do quite a bit in our university. We do field experiments, which basically nature tells us what is right and what is wrong with the various simulations, and computer simulation through computational fluid dynamics, which more recently, has been given a lot of emphasis, and Mauritius' work was all dedicated into that. So let's start with the empirical models to give you an overview, and let's start with the ARSST dispersion models. Basically, ARSST has two approaches: the old geometric design method, due to Professor Wilson, actually, from Canada, and the Gaussian plume equations for roof level dilutions. And of course, there are advantages and disadvantages. I'm not going to go to all the details here, not to tire you, but you're going to see that this method makes some assumptions. For instance, make the assumption that the plume comes from the stack here at the slope of 5 to 1. Then you see that you have the recirculation area, and this assumes to be, we assume that this is 10 to 1, and then we try to see where is the kind of, the intersection. That's point A here, and then you say this is a critical area. So by changing, let's say, the height of the plume, you can change the location of this point A and make sure that, depending on the geometry, that basically you are not going to have pollutants in the areas where you want to put the air inlets. It's as simple as that, not very accurate, of course, but basically it has to do with the so-called effective height of the plume, and this is expressed with these simple equations, only simple equations I'm going to present today. Okay, so basically the effective height of the plume is equal to the stack height, to the plume rise, which is given by another simple equation here, due to Briggs in 1984, and reduced by the so-called, there is a reduction in the plume height due to the entrainment into the stack wake during periods of strong wind. The second model is the so-called Gaussian plume model, and this one is kind of, diagrammatically presented in this graph here. Again, this is not a complicated equation. This is the equation of an exponential. As you can see, it's an exponential equation. So we assume that when the plume comes out here, really by the influence of the wind coming in that direction, really travels in this way, and on the basis of this equation, we can calculate the dilution, which is thus the ratio of the concentration at the exhaust over the concentration at any point on the roof that we're interested in, and this is going to give you what the actual dilution is. They are very simple models, of course. You can see what is happening. You can apply the equations. You can get, a curve like this here, and this is the ARSST curve, which tells you basically how the dilution changes with distance on the roof level. Keep this easy kind of curve in mind for reference, because we're going to compare this kind of curve with additional cases when we try to assess the pollutants by using other methods in order to see really where we are. So going back to the ARSST dispersion models, what are the merits, what are the demerits, what are the advantages, what are the disadvantages? Well, the advantage is that they're easy to use for near-field dispersion problems of isolated buildings. The disadvantage is that they do not consider effects of building geometry, just you have one equation for any building, surroundings, which is very important, wind direction, which also could be extremely important. But in general, and that's the way they should be, they are very conservative for dilution prediction. Now, the problem here is this very conservative. To be conservative, any model should be conservative when it's going to be used for practice. To be very conservative, of course, that gets uneconomical sometimes, and I think that's one problem. Now, empirical models, EPA, there are a number of those, and this is just a list. I'm not going to go through all of them. The only thing I'm going to tell you is that with some slight variations, that these models are based on Gaussian distribution. And in fact, we have done a study, again in collaboration with IRSST, to see the effectiveness of all these models. And if you do this study, you're going to be able now to compare some of the results that we kind of get for different models, and also the results from the wind tunnel that you see here. So there are variations. Some of them are higher, some of them are lower. Okay, they're closer to the wind tunnel, they're further away, but of course, for different cases, you get different results. Again, what are the advantages? Fast and easy to use. They are suitable for isolated stacks. Some of these models, like the Adams and the Kalpoof models, can model building and stack downwash effects, and that's very good. The disadvantages: most models predict very high concentrations within the first 10 meters from the stack, and this is what we're interested from the building engineering viewpoint, building design, okay, and they could be unsuitable for near-field dispersion pollutants. And also when you have complex adjacent buildings layouts, which is what's happening in a city normally, then of course they are weak to kind of model that. So we leave these models now and we go to the lab. We go to the actual experiment, measurements. And in fact, that's the most reliable. Even today, that's probably the most reliable. Could be contradictory, but that's the most reliable methodology here. Here you see a photo of the boundary layer wind tunnel that we have at Concordia University, with one building here, isolated building in the middle of nowhere. We use buildings like that for code purposes to get worst case loads and so on. The wind tunnel, basically what it does, it simulates physical simulation of the wind flow around building models. It requires a particular geometric scale for modeling the building and the surroundings, and this is the same scale that we model down the wind. So basically we have to have simulation. We try to trick, if you like, the building. So we make a smaller building, okay, and we have a smaller wind, let's put it this way. And that's very, very good for studying wind building structure interaction problems, whether this is wind loads on buildings, where it is pedestrian comfort, ventilation, dispersion in this case, and so on and so forth. So wind tunnel modeling, this is just an example here, and I use the same building that we used before for comparison purposes, because now you can see here what is happening. That was the previous curve that I told you to remember. So it's here, and this is now the wind tunnel results. So you can see that there is a discrepancy here, but of course the dilution is higher, which means that the concentration is smaller, which means that actually is conservative, quite conservative, I must admit. Now, the advantages of wind tunnel modeling, well, we take into account the effects of surroundings, so we can really simulate a real case. We look at the local topography, we look different upstream conditions, we can have different winds, different turbulences, and so on. It is the most accurate method of predicting dispersion of pollutants today. It's not the least expensive, of course. Now, what are the disadvantages? Well, the disadvantage is that sometimes we may need to have building models of large scales, and of course this can block the flow. You see, the wind tunnel is supposed to represent what's happening outside, but outside we say the sky is the limit, right? There are no walls, there are no ceilings. The wind tunnel, we have walls and we have ceilings, so we have to make sure that the model is very small in comparison to the space, otherwise the results are not going to be representative. When you have buildings with curved surfaces, then they are very difficult to be modeled, because we have some Reynolds number similarity restrictions there. When you have architectural details that they could be very important for the local flow regime, like we have balconies, we have rooftop structures and so on, again, these are maybe difficult to model. So there's nothing perfect, there are difficulties there, that's why researchers struggle with that. Field experiments. Well, now we go to the real world, so nobody can argue with nature, okay? So the good thing is that this is real wind, this is what is happening in reality. Of course, we have to deal with existing buildings. So as far as design is concerned, that's not going to be very good, right? Because I want to design the building before it's built. When it's there, well, it's too late, okay? So, or I have to change it, and that's another big expense. So field experiments are valuable, but they are valuable mainly because they can validate particular experimental data and help to improve simulation conditions and methodologies. That's the main kind of utilization of field data. We use an anemometer to estimate wind velocities and directions. We use tracer gas techniques that they release from a stack. And of course, we have collections of air samples that we analyze them in order to measure concentrations and dilutions and whatever else we want at various locations. Again, we were very fortunate to carry out a study with IRSST where we managed to kind of, put on a real building, put stacks, artificial stacks at various locations, so we could see the effect as to what is happening. So this is the building that we used. That was the old Center for Building Studies building that we had. That was a rented building, but we were given permission to put stacks on the top of the building, and that's what happened here. So you have now the stacks at various locations. These are artificial stacks. We put them there: SL1, SL2, SL3, SL4. So basically, for different wind directions, we could see what was happening, and then we could compare the results with the models, with the wind tunnel, and so on, which gives us valuable information. That's how it looks like. It's a very simple kind of thing that you can move it. Louis Lazour was very instrumental in that, and this is some part of the experiment. So, field experiments, what are the advantages? Reliable results, since measurements are carried out in actual conditions, absolutely necessary for validation purposes. Disadvantages: they're very expensive, they depend on the weather, they are difficult to carry them out, you have to be very patient, because they are weather dependent, you may have to wait for a long time for the wind to come from the right direction for you, okay, because the wind comes from the direction that it wants to come and with the intensity and the magnitude that it wants to come, right? They don't get permission from us. Okay, so last but not least, CFD. I don't know how many of you have kind of, worked or heard about CFD. It's in wind engineering, we call it CWE, which is computational wind engineering. It's basically the same thing. So we're talking about now numerical simulations with all the progress in the computers and so on, and that's what Mauricio did all his work. So what we do here is we try to represent the details of the flow. It's easier said than done, okay? The Navier-Stokes equations are kind of complicated equations to be simulated. We do use special computer programs. We try to develop our own. We had our problems. Then we use some commercial codes like Fluent. You have different problems there, and so on. So what we're trying to do, of course, and that's the advantage of that, is you try to kind of, obtain the flow properties, and then, of course, the dispersion. I mean, when you have the pollutants involved at every point simultaneously. The application is not simple. Now, very quickly here, just to give you an overview, I mean, when we do CFD simulations, these are the 6 kind of, areas or the 6 items, let's say, that one has to pay attention to: the domain, the model, the grid, the equations that we use for flow and dispersion, boundary conditions, and convergence criterion in order to solve the equations and get the solution. When we talk about the domain, there was a very interesting reference a few years ago that basically talks about different length scales. We have the regional length scale, the city, and give you the dimensions, approximate dimensions here, the neighborhood scale, and the street scale, which is less than 100 to 200 meters, which is what we are interested in. So basically, we're dealing with a situation like that. You see some parameters here as to what the domain is going to be, and these have come out of detailed studies that they kind of, have taken place in various places in the world to see what we really need for that. I mean, each of these items, I'm just going very quickly through them now. They're very kind of, complex. This is the physical model that we have, where we kind of, we can put, of course, anywhere we want the release, that of the gas, whatever. We can put the receptors anywhere that we want because we model the whole situation here. This is an example for the 2-building configuration. To go from 1, you go to 2, and then to 3, and then you go to many. Don't go to 4, 5, 6. Okay, so that's how we kind of proceed. The scale that we use is about 1 to 200. That is the scale where we scale down the wind, the characteristics of the wind, okay? And we use concentration here, and we use the height stack. As you can see, that's in the wind tunnel scale, the experimental scale, and this is what that corresponds to. So this is the grid. Now, the grid defines, of course, the spatial resolution. The more points you have, the better it is. But, of course, the more expensive the solution is. And what you have to do to avoid inaccuracies is you have to have a small kind of, high density of points when you have high gradients, or where you expect to have high gradients of the flow or the dispersion. The expansion ratio between 2 cells should be below 1.3. Now, there are all sorts of conditions in the literature to go through, and we always recommend to have a grid sensitivity study and see whether or not, let's say, because you got some results because you got a particular grid, and if the grid had been different, the results would have been different. Now, that's a very complex slide, but basically it tells you something as the so-called Reynolds average Navier-Stokes equations, how you try to model it, to describe with equations the conditions of the flow. And there you have something which is called turbulence, fluctuations of the flow, and turbulence is very complicated to be modeled, and that's why there have been a number of models in the literature, and from the simplest one that you can see here to the more complicated one, which is probably this, because that takes into account the anisotropy. If you remember from physics, isotropic phenomena, anisotropic. Well, I mean, all these models assume isotropic turbulence, isotropic phenomena. This one takes into account anisotropy, and anisotropy is closer to reality, so it's a little bit more accurate, but more expensive as well, right? I mean, you always pay price for that. That was for the steady simulations. Now, for unsteady simulations, there are a number of techniques, starting from the direct numerical simulation, which is still, for actual real cases, unapproachable today. We go into the large eddy simulation, which is being used quite extensively today, and it's probably the most accurate approach, but expensive to use. We have the detached eddy simulation, where it's a hybrid kind of technique. It's like something, the hybrid ventilation that you're familiar with, and so on. That's the same type of approach here. And then we have the unsteady Reynolds average Navier-Stokes equations, which again, it's a simplification, of the previous techniques, but they don't always work in the best possible way. There's still a lot of research that is going on into these areas. Now, boundary conditions, of course, every time that you have a numerical solution, you have to have some boundary conditions. Perhaps I will draw your attention to the inlet, okay, where you have the wind velocity profile, turbulence intensity profile, so that what you are going to calculate is going to represent an actual situation as to what environment we have. And then, of course, we have on the computational domain, we have various boundary conditions at the outlets and so on. Convergence criterion, we always need one, and again, this is just 3 lines here to remind people that the conversion criterion that we use is based on residuals of equations, which are designated as to how far the current solution is from the exact solution and how you kind of approach that. It has been a study that has shown that for studies of this nature, urban studies as we call them, that 10 to the minus 5, it's a very small number, is a good number, but some cases may need less than that. And again, this is just an example where we have the steady approach that I mentioned before. We look at the effect of turbulence models, because you see, you have the luxury here that you can try different models and then get the results. And at the same time, you see here that we have the wind tunnel kind of results. As I said at the beginning, we trust the physical simulation more. And you can see here that the closest to the physical simulation are, the stack is right here, are the results from the renormalization group, the RNG, that what we have, the other kind of turbulence models gives you higher distances. And again, this is kind of an example. As I said, not all cases work this way. Now, what is important is that after we have some confidence and some trust to the CFD approach, then we can follow up with a parametric study. Now, a parametric study is something very, very important, because it may help us to go into the objective, the final objective that we have, which is to help the practitioner. And to help the practitioner, we have to determine some design guidelines. They are coming up, okay? So we want to do a parametric study, and the parametric study basically looks at some particular configurations, and we selected the ones that you see here as basic ones. So here is the emitting building. Here's when you have a building upwind, if you like, for this wind direction, okay, upstream. Here's when you have a building downstream, and here's where you have 2 buildings, okay? So basically one upstream and one downwind, and then see what is happening, with that. Of course, now everything that you see here is a variable, so we have height, width, length, spacing between buildings, and so on, different parameters, so that you can see how the dispersion kind of, develops, or the concentration, same thing, how they develop for different cases. And this would be very important to come up with some design recommendations. So you see where we're going now. Follow me. Okay. So let's look at the parameters here that we have. Too many numbers here, but this is just to show you the different cases that we have examined computationally, okay? And in total, there were 29 cases that they were simulated. It's quite a high number to really cover a number of realistic conditions, realistic situations. Now, these are some of the results here when we have an upstream building, and whether you want to see what's happening. I know it's very complicated, too many kind of, graphs here. Again, the old IRSST model. Remember the curve that I told you at the beginning to remember? Okay, so basically this is this one, the blue one, whatever it is here. And then you see it's still very conservative here, even when you have this situation. That's good, in a sense, to know. And this is what is happening now for the various kind of cases. And you can see that as you increase the distance here, and here you increase the height of the building here, you can see that the dilution increases. Here it decreases, but to a lesser extent. So all these things, of course, have to be analyzed. We have done that he has done that, okay, to really see what is happening here. And another case that you look now into the case of we have the 3 buildings, okay, and you see again what is happening with the dilution, what are the contours, what is the distribution, and how they develop along the axis of the roof and the walls and so on. And here you see again this kind of for the various parameters here, what is the tendency is here to increase, here to decrease a little bit. So that gives you an idea as to what's happening, and that takes us now to the design guidelines. Now, a little bit of history here. And if you look into that, you're going to see, first of all, we start with the most generic to go to the most specific, okay? That's the approach here. So we're looking at the Quebec law, and the Quebec law says something very interesting. The only comment that I have about it is, in other words, there's nothing new there. What it says is clearly motherhood statement. It says that the regulation respecting the quality of the work environment stipulates that fresh air intakes must be located so that no air already evacuated from an establishment is reintroduced. Yes, I agree 100%, but I think everybody would agree without any study before even starting anything, right? So basically, it states the obvious. It has to be stated. It's the law, okay, and so on, and that's what we're trying to do. It doesn't tell us how we're going to do it. That's the problem, okay? Now, we do have, however, other existing codes and standards, quite a few actually, and I have put them together here. And it says here, for instance, we have the American Industrial Hygiene Association, which basically recommends, now it becomes a little bit more specific. That's a little bit more useful, I think. Okay, it says a minimum stack height of 10 feet above the adjacent roof line and extending 1 stack diameter above any architectural screen. Minimum exit velocity should be 3,000 feet per minute. This is useful for the designer to do. It doesn't cover all cases. It doesn't cover different wind directions. It doesn't cover whatever, we try to cover with other methods, but definitely is kind of useful. The same thing with the rest that you have here. Okay, the Uniform Plumbing Code requires exhaust vents to be 3 feet or more above air inlets. So all these are kind of enveloping conditions. The National Fire Protection Association gives another kind of standard 45, specifies a minimum stack height of 10 feet to protect rooftop workers there. So there are different reasons that, they are being forward. The Uniform Mechanical Code, widely in the USA, is being used. It recommends exhaust of at least 3 feet from property lines and 3 feet from openings into the buildings. Again, useful information. It doesn't cover all spaces, all the cases, but basically, and here's another interesting suggestion here, which says that you have to place air intakes on building side walls. The only problem with the side walls is what happens when the wind comes from the other direction, but that's another issue, assuming that the wind comes primarily from one direction. And what about ASHRAE? We talked about it before. Well, again, ASHRAE has provided over the years some interesting and useful, I would say, recommendations. Again, the only problem is that all these recommendations are good, but they are good for isolated buildings, and you rarely have an isolated building. In reality, you have more buildings. So that's the point that we're trying to make here. Now, if we talk about additional guidelines, they are based on the studies that we have been carried out here. So, and we kind of, have these additional guidelines organized in terms of the stack, location, height, exhaust momentum, and so on. This is the ratio of the exit velocity over the wind speed in order to avoid recirculation areas, which are the ones that they're going to make the pollutant re-ingest, because the wind takes it and brings it back. And also in terms of the safe placement of intakes, that's what the practitioner wants to know. Where should I put the intake to avoid re-ingestion of pollutants? So we do that in these 2 categories, if you like. First, in terms of stack location. And here is now the particular cases that we feel that they may be very useful to designers if we have, let's say, an open FET situation, or if we have a taller building at stream, and then we have some kind of, sometimes qualitative, sometimes quantitative kind of, statements to really say what we should avoid and what we should kind of, go for. Okay, so there are a number of those. I want to go through all the details, but basically, I want just to show you, to give you a flavor of the organization of that. So if we have now X is an important parameter, what is X? X is the distance from stack to the sampler, from stack to the intake, okay? So basically, if it is, and that's based on the results of the study, if it is less than 20 meters, or if it is more than 20 meters, okay, this is some guidance, okay, as to what is happening if you change the parameters. And that's useful to know, because also there is a cost involved here, so you have to take these things into account. Now, again, this has to do with the exit velocity that you're going to have there, and so on. Now, if we look in terms of safe placement of intakes, like where should I put the intakes and so on. Now this is always a problem if you think about it, which always worried me. And this is because really the actual kind of criterion that you have to use here depends on the actual substances. And the substances will be different from building to building, and depends on the utilization of the building from case to case, right? So how do we go about it? Well, again, engineering always has to find solutions, cut corners, we call it, and so on. And what has happened here, and this is a very valuable criterion which is being used today, they're using this criterion here and say this is now a criterion that if you want to avoid odors and occupational health effects for a large group of chemicals, so we go to a large group of those and we say, okay, assuming that you don't have only one and very kind of, critical one, then what you're going to do here, and this is what experience has shown, that this is a very good number, a very good number for the dilution. So if you take that and you normalize the values, you end up with dn is equal to 6. So this 6 comes from this ratio here if you put the actual parameters that we have there. So basically this is very good for the establishment of guidelines, even in a nice visual way, which is something that I think most practitioners appreciate. So here it is now for the safe placement of the intakes for different configurations. What we do here is we use this magic value of 6 with the understanding that this is an average value and it may not work in all cases, particularly if you have some special circumstances, special conditions. So if we have this kind of, iso contour here, iso surface with 6 there, then of course here is a clear zone, here is the dangerous, if you like, zone, so I'm trying to avoid whatever I have here. So I have, let's say, this main wind direction, I have a building here which is equal height, okay, and this is the situation. Now I know what to do as a practitioner, very easily. If I have a medium tall building, okay, so this is something that's, let's say, 1 story taller than the emitting building. These are all approximate kind of, guidelines. Then that's the situation, okay? So I have kind of, more restrictions here, but again, I can see what I have. If I have an even taller building upstream, then I have, of course, a much more difficult situation. What that curved surface tells me here is avoid that area completely, put whatever you have to put there. Still, it's very useful for design purposes. I hope you'll agree with me. And here's different cases now, okay? So here is now the safe placement of the index for different spacing. If I have 50 meters, if I have 35 meters, if I have 20 meters equivalent, and you see how different, things become. Again, this is something very useful to know. If we have the downstream building, remember all the configurations that we had, so this is what was for that purpose. If we have the downstream building, you get something like this here. And finally, if we have the 3 buildings together, this is the picture that, it appears based on the parameters that we have examined. So, if I want now to summarize and conclude, basically what we talked about was empirical models, ASRE, EPA. They are questionable for the assessment of pollutant concentration in the vicinity of buildings. They may be suitable for isolated buildings, but not for many more than those. Wind tunnel test results derived with correct simulation conditions are reliable, particularly when validated with field measurements. Field experiments are costly, time-consuming, but absolutely indispensable for validation purposes. Steady CFD comparison with wind tunnel data show that RANS, the Reynolds-Haber-Navier-Stokes equations, underestimates dilution within the wake area. We carried out a parametric study using steady CFD that allowed us to quantify the effect of various adjacent buildings on dispersion. We have developed some guidelines we feel very useful to avoid the reingestion of pollutants for non-isolated building configuration, and these guidelines are given in terms of stack characteristics and safe intakes location. We produced a number of journal papers, 2 PhD theses that I mentioned before, several conference papers, and technical reports that they are, most of them, if not all of them, are available or will be very shortly available on the website. And now just a word only for future research. Of course, what does it remain now based on all this discussion? Well, some more complex configurations. And we do have models. You can see another kind of situation here. And what we have to do now, which is the next step, is go and check and see whether the guidelines that we developed are going to be good enough for a real situation that's more than 2 or 3 buildings and so on. So The other thing that we intend to do, just to give you an idea, is we want to go forward now with this work, with whatever we have learned here, and try to do some particle tracking by using biphasing approach, the dispersion of droplets. And this is because, again, it's engineering research. We try to really reflect on what has happened and try to help these situations not to happen again. And of course, you remember what happened in Quebec in the summer of 2012. Okay, there where at least 180 people were infected, 13 were killed in what has been the deadliest outbreak of the Legionnaires' disease in Canada in 25 years, we understand. So we're trying to do some work now to see what else is required to avoid problems like this from happening.